In this next video, we're going to talk about vapor-liquid equilibrium, but with multiple components. So this is multiple chemicals. This could be methanol and water. It could be ethanol and water. It could be methanol and ethanol. It could be benzene and toluene. It doesn't matter. It could just be a mixture of many components. And oftentimes we refer to a binary mixture as one that has two components, binary being two. And really in this course, we're really, for the most part, going to deal with binary mixtures. We may branch off to mixtures containing more than two components, but most of what we deal with is going to be binary mixtures. So I have here an example where I have a component A in liquid phase, and then above it I have some vapor, and each one of these dots just represents a molecule of that particular chemical. And then I have B over here. So I have B in the liquid phase and then B in the vapor phase. And the liquid and the vapor are in equilibrium, vapor and liquid equilibrium, and you'll notice, for instance, that there's a lot more B in the vapor phase or gas phase compared to A. So we have less gas molecules of A. So we would tend to say that B is more volatile than A. So B is just a more volatile, so its vapor pressure is higher. Now what if we take a mixture of these? So what if we pour A and B into a beaker and mix them together? So we have a mixture of components A and B in the liquid phase. Well, we're also going to get some molecules in the gas phase of A and B, like I've shown you right here. And this equilibrium between this gas phase and this liquid phase is what we're going to be concerned with for the remainder of this video, and really this is going to be a big concern of what we're going to focus on for a large portion of this next part of the course. What is the equilibrium between this gas phase and this liquid phase when we have two components? Now let me just point out that when we have two components, the chemistry of those molecules, or the interaction of those molecules, can change the vapor-liquid equilibrium. So when these molecules of B and A interact with each other, that can change how volatile these molecules are. So for instance, here I show you 5 A molecules in the gas phase, whereas here there's only 3 A molecules in the gas phase. And that's because when we put this mixture together, the volatility of the A molecules changes when they interact with the B molecules. And so it does get a little tricky when we're dealing with vapor-liquid equilibrium of mixtures, but we're going to walk through the steps and the various concepts that we have to work with, and it's not too tricky once you understand things how they work, but we just have to be aware that single component vapor-liquid equilibrium is different than multiple component vapor-liquid equilibrium. And so let's just look at an example here. We have a mixture of components A and B here in liquid phase, and then we have some of that A and B in the gas phase, and these two are in equilibrium with each other. And because of the interactions between the molecules, there is a particular mole fraction of one of these two components. There is a mole fraction in the liquid phase for component A mole fraction in liquid phase for component B, and then we also have we could potentially have a different mole fraction in the vapor phase for A and a different mole fraction in vapor phase or gas phase for component B. And so what I have here is I'm going to draw a plot of the mole fraction in the liquid phase for the more volatile component. So let's just say this is A. A is more volatile than B, which means A likes to be in the vapor phase. It wants to be in the gas phase more than B. So on the x-axis, we have the mole fraction in the liquid phase of the more volatile component, in this case A. Y-axis, we have the mole fraction in the vapor or gas phase of the more volatile component. Again, that's A. And if we plot that, we'll get something like this. We'll get a plot that looks something like this. So let me just further write something down. This is oftentimes referred to as X, and this is often referred to as Y. When we make this kind of plot, it's called an XY plot. And X is simply the mole fraction in the liquid phase. Y is the mole fraction in the vapor or gas phase. And so that's why we call it the XY plot. because we're plotting the mole fraction in liquid versus mole fraction of vapor. So this plot right here just has this curve here, and oftentimes we put a reference line on these XY plots. And I've shown this reference line, which is just a straight line, and it's the y equals x line. And what does that y equals x line mean? Well, the y equals x line is simply the line where the mole fraction in the liquid equals the mole fraction in the vapor. So in other words, it's the when the mole fractions are equal to each other. So we just draw this, usually on these XY plots, just as a reference to help us understand the plot a little better and follow it a little better. We don't have to put them on the plots, but we just draw them for helping us understand the plots. So I draw this here, the y equals x line, right here. And here's the curve of the vapor-liquid equilibrium. Again, this is the mole fraction in the liquid versus the mole fraction of the vapor for the most volatile component, in this case A. And what do we see? Well, in all cases, this line is above the y equals x line. So in every single case, y is greater than x. So what does that mean? Y is greater than x, because again, we know this line is above the y equals x line, so y is always greater than x. Well, that means that we have more in our vapor phase of component A than we have in the liquid phase. So the mole fraction it's a greater concentration in the vapor phase or gas phase compared to the concentration in the liquid phase. And that's always the case when we have these binary diagrams, two components for the more volatile component. The concentration in the vapor phase is always greater than in the liquid phase, just like this plot shows us here. Y is always greater than x for this type of material. So I just showed you the plot where we put the mole fractions in the liquid and vapor phase for the more volatile component. What about for the less volatile component? In this example, this would be component B. B is less volatile than A. Well, here's the plot right here, and again, I've just drawn the y equals x line as a reference line, and what happens is, or what we observe is that the mole fraction in the vapor phase is always less than the mole fraction in the liquid phase. So x is always greater than y. Or in other words, there's a greater concentration of component B, or the less volatile component, in the liquid phase compared to the vapor or gas phase. And so this is very similar to the previous plot, except it's just inverted. We have more of the component B in liquid compared to the gas or vapor. And so these two plots, they're both XY plots, they just tell us about the relative concentrations in the liquid and the vapor phases. So, for instance, if I ever want to know what the concentration again is in the vapor phase, I can just match it up somewhere along here on the liquid phase. If the liquid phase concentration is right here, well then I just read up here and then read across to get it what it is in the vapor phase. And so they're very useful for defining the properties of the vapor and the liquid phase. Now let me just say one caveat. I've shown you here, this is the plot for the more for the less volatile component, where it's down here and it's below the y equals x curve. We often in reality don't deal with these type of curves that often for the less volatile component. Our more common plot that we deal with is the one I just showed you, where we have the x and the y, or the mole fractions in the liquid and the vapor for the more volatile component. That's the one you'll typically see. That doesn't mean we won't see this type of plot where we have plotted the less volatile component. It's just less common. So we often will deal, as I said, with the plots where this curve is above the y equals x line, or it's for the more volatile component. And to be honest, once we know what the vapor or the mole fraction in the vapor or liquid phase for one component, we know what it is for the other component, because it's really easy, because the sum of the mole fractions are equal to 1, like I've shown you right here. If we add up the mole fractions in the liquid phase for component A and component B, they equal 1. If I add up the mole fractions of component A and component B in the gas phase, they add up to 1. And so if I know XA or I know YA, I can just find XB and YB using this equation right here. So again, we often will only have to deal with one of these plots rather than dealing with both because of this equation right here.